Hi, I'm Diane Moug from Portland State University. Today on summer school, we're going to the beach for cone penetration testing. Hi, I'm Diane Moug. Welcome to summer school. This week we're talking about the cone penetration test. So, getting started. We're going to start out, in order to talk about the cone penetration test, we have to talk about geotechnical site investigation. So we're going to start off with an overview of geotech site investigation, then get into how we use and operate the CPT, the cone penetration test. We'll start interpreting CPT data, primarily stratigraphy and soil behavior type. We'll talk a little bit about soil property interpretation, and then we're going to finish with an example in a collab. So, starting off with geotech site investigation. Geotech site investigation is a critical part of almost any project. As Richard Handy said, virtually every structure is supported by soil or rock. Those that aren't either float, fly, or fall over. So we need to get the soil and rock right in order to properly build on or in them. So what are our goals of site investigation? We want to establish a model of subsurface ground conditions. That model needs to have soil, water, and rock data for design, construction, and analysis of the structures, including the properties that we need for the analysis and design. We're going to use the model and site investigation to identify potential geohazards. And then if we're in the case where a project requires construction with that soil or rock, we're going to be able to characterize the construction properties of that soil and rock. When we go to approach and plan a site investigation program, we have a toolbox of various tools we can use or approaches we can use for site investigation and to build that subsurface model. One of the first tools we'll use is a desk study. And this is taking all available information that we have about a site. That includes geologic maps, aerial photos, Google Earth images, past project reports, nearby projects. How did they perform? What kind of design did they use? LiDAR, maintenance records of the area, anything you can get your hands on that gives you some information about engineering and the subsurface in the area. Then we have the tool of sampling, drilling and sampling, where we get soil from the ground and we take it back to the lab to classify it or to test it and characterize the engineering properties of that soil or rock. This includes the SPT, Shelby tube sampling, sonic drilling, all with various advantages or disadvantages or ways that they capture and preserve the soil. Then there's in situ testing. This includes the CPT, the cone penetration test. In situ testing, we're not getting any soil, we're not sampling any soil, but we're disturbing the soil or loading the soil in a way to see how it responds, and then we're interpreting behavior and properties about the soil. And finally, geophysics as our last tool. Geophysics, we're not obtaining any soil. We're also not disturbing the soil. And we get an image or other information about the way that the soil responds to the signal that we send through it. And this includes electrical resistivity, seismic velocity surveys, ground penetrating radar, and other tools. And so the cone penetration test is one tool in our site investigation toolbox. And with the CPT, it is an imperfect tool like all other site characterization tools. But by using these tools and understanding the limitations and the advantages of these tools within the project context and the objectives of the project, we can approach site investigation and characterize the subsurface. And so this is an example of what the CPT looks like as it's deployed on site with a CPT rig, the cone itself, and then some of the data that we get from the cone, a depth profile of data, along with some lab testing data. So now into the overview and operation of CPT, our site investigation tool. With the cone, I actually have an old cone right here. The cone is hydraulically advanced by a truck through the subsurface in a vertical profile. It's pushed at a rate of about 20 millimeters or 2 centimeters per second. And we get a nearly continuous data profile. The readouts of the data from the cone are taken about every 5 centimeters. So we get this nearly continuous data profile, and we can profile routinely about 30 meters in depth, and with a bigger truck, larger capacity, we can get up to 200 meters. The cone is generally pretty economic, both from a time and a cost standpoint. We can profile a 30-meter section depth of the soil in about an hour. So within one site, you can get multiple cone profiles within one day. The standard operation of the cone is referenced in the ASTM D5778. The cone itself, the main measurements in the data that we're collecting from the cone as it's pushed through the ground, we're collecting a cone tip resistance, sleeve friction for the shear that develops along the cone, and then we're measuring the pore water pressure as it develops at this U2 position, right above the cone shoulder before the friction sleeve. Inclination of the cone is also measured. So in these data profiles, we're looking at cone tip resistance, sleeve friction, and pore water pressure measured at the cone shoulder or U2. This value, QT, is the corrected cone tip resistance. It makes a correction for the little bit of pore water pressure that acts back down on the cone tip in reverse of the upward reaction of the cone. That correction factor A is typically about 0.8. And then this image here from our site up in Northeast Portland, it shows one of the other advantages of the cone is that you get a readout of the data right there in the field. And also because you're collecting digital data, the processing and the issuing of the report of the CPT data happens fairly quickly. The cone itself, the CPT, is appropriate for sands or applicable for soils from clays to sands. Anything coarser than sands, we can't reliably interpret the CPT data. Typical geometries and sizings of the cone. For engineering practice, we are typically using a type 2 cone, meaning that it has the pore pressure element right here above the cone tip. And then the sizing of the cone standard is a 10 centimeter squared or a 15 centimeter squared cone with diameters of 35.7 millimeters and 43.7 millimeters, respectively. And then they both have this 60-degree apex at the cone tip. As with almost all things that we do in engineering and data collection, we do need to take steps in order to collect high quality or reliable data. And so these are some of the steps that we use in our standard operation and procedures of the cone to try and get the highest quality data that we can. First thing is that any cone profile should be at least 25 borehole diameters from existing boreholes, so that there's a spacing between the profiles, so that the cone profile isn't being pushed through soil that's been disturbed by drilling. With the cone, you want to take baseline or zero readings both before and after the cone is pushed through the ground to see that cone tip, sleeve friction, and pore water pressure, the differences between the before and after are less than 2%. The cone, after it's been pushed for hundreds and hundreds of meters through the ground, through clays, silt, sands, it starts to wear down. And the cone sleeve and the cone tip themselves are disposable and should be replaced. And that's how I ended up with this. And so once they're worn down to the point that they're outside of the ASTM standards and the compliance, as shown in these figures for the 10 centimeter squared and 15 centimeter squared cones, then they should be replaced. The measurements are given on this diagram. When you're out in the field, one of the data checks you can bring calipers out there with you. Good thing to have in your site investigation toolbox. You can also get these templates that give you the standard measurements to see whether your cone meets those compliance measurements. Pi tape is also useful to have to see that the diameters are within compliance. And when they're outside of it, they should be replaced. The O-rings and seals within the cone between the connections should be replaced regularly so that soil doesn't get into the cone. The filter element that connects to a pore pressure transducer should be properly saturated. There's procedures in the ASTM standard for that saturation procedure. And then as the cone's being pushed through the ground, we mentioned that inclination is one of those things is set as data that should be collected. It should be monitored to see that the inclination does not exceed 5 degrees over 1 meter or 12 degrees over 10 meters as the cone's pushed through the ground. So we get the CPT data. We're getting cone tip resistance, sleeve friction, pore water pressure. We're correcting cone tip resistance with that area ratio. Now there's variables that we're calculating from the cone data. These include delta U2, excess cone shoulder pore pressure, friction ratio, the ratio between sleeve friction and cone tip resistance, normalized cone tip resistance to account for effective stress and how cone tip resistance changes with effective stress, effective cone resistance, QE, normalized sleeve resistance, FR, and the pore water pressure parameter, BQ. These are all standard parameters we calculate from the measured CPT data that we use to interpret soil properties and soil behavior type. So this is here for your reference. We have that data, we do that initial processing of the data, then we move into interpreting stratigraphy and soil behavior type from our cone. And stratigraphy interpreted from the CPT is one of the advantages of the CPT. Because we get that nearly continuous profile of data, it is advantageous to see where there's changes in the data reflecting changes in stratigraphy or soil properties. So we can detect primary stratigraphic units in those data profiles. We can also, with the pore water pressure measurement U2, estimate the location of the groundwater table from CPT data. So when we think about the stratigraphy from the cone, there's some rules of thumb. If we're pushing through a clean sand, the cone tip resistance tends to be high. It's harder to push through sands than through clays. So the cone tip resistance then reflects that through a tip resistance of greater than 5 MPa. The friction ratio plotted here is typically less than 1%. For sands, meaning that friction relative to the cone tip resistance is lower for sands. And in sands, any pore water pressures that are generated by pushing through the soil, by compressing it, shearing it, failing it, any pore water pressures that are generated are dissipated away quite quickly by the cone in sands. So the pore water pressures are dissipated faster than they're generated with sands, and therefore we end up with a drained condition in sands. And for that reason, the pore water pressure at the U2 tends to just read hydrostatic conditions, or U0, reflecting the hydrostatic pore water pressure of the groundwater table. On the other hand, for clays that are soft to firm to stiff, intact clays and silts, cone tip resistance tends to be less than 5 MPa. And with clays, because clays have relatively low permeability, any pore water pressures that are generated by the clays are not dissipated or consolidated as quickly as they're generated, and we tend to have undrained conditions for penetration in clays. So we measure U2 pore water pressures that are not equal to the static pore water pressure. And how much larger or less than the static pore water pressure they are is an indication of the consistency of the clay, where soft clays tend to have a U2 pore water pressure about 2 times the static pore water pressure, up to stiff clays where it's about 8 times. And then if you have fissured and highly overconsolidated clays, the measured U2 pore water pressure can be less than the static pore water pressure. Friction ratio for clays tends to be greater than 1% for insensitive clays and silts, indicating that the sleeve friction is relative to the cone tip resistance is high compared to sands. If you have organic clays, the friction ratio is high, about 8%. But if you have sensitive clays or quick clays, an indication of that is a very, very low sleeve friction, much less than 1%, because by the time the soil has moved around the cone up to the sleeve, it's gone through quite a bit of shearing and lost the strength, reflecting its sensitive clay nature. So some rules of thumb. for stratigraphy. And you can see those here on the example data from the Cone-Tech manual. You can see where there's these deflections or changes in the cone data indicating a change in stratigraphy. In this upper part here, cone tip resistance greater than 5 MPa with these layers, a lower friction ratio, and pore water pressure that's about equal to hydrostatic, indicating sand. Then we move into clay with a low cone tip resistance, higher friction ratio, greater than hydrostatic pore water pressure, and then back to sand for this layer, where we see those indications of a sand stratigraphy. That's stratigraphy. Then we have soil behavior type. And these are correlations that relate the measured CPT data to known soil profiles to get our soil behavior type correlations. So we're taking the CPT data that we measure and correlate it to the most likely soil behavior type. I'll note that with the cone, of course, we do not get a soil sample, so we're not getting a proper USCS or ASCE classification of soil. Therefore, we are calling it a soil behavior type as opposed to a soil type or soil classification. There's several different interpretations of soil behavior type. This is one of the common interpretations where the normalized cone tip resistance and friction, sleeve friction are related together, and then they correlate to various soil behavior types based on where they fall on this plot. Same goes on this complementary plot, looking at normalized cone tip resistance versus the pore water pressure parameter, BQ. And so on these plots, depending on what zone of the figure the data fall into, that correlates to soil behavior based on the zones that are classified here. In this upper left corner of the plot between cone tip resistance and sleeve friction, porous soils, gravelly sand to sand for zone 7. They plot up here with a pore water pressure parameter close to 0 and high cone tip resistance. And then as you move down to higher sleeve friction ratio and lower normalized cone tip resistance, we're into organic soils and peats, which also plot down here in the BQ cone tip resistance plot. From those plots, you can also relate where the soil falls in terms of cone tip resistance and normalized sleeve friction. That can be related to I sub C, the soil behavior type index. And what I sub C represents is the distance from this focal point on the soil behavior type plot. So those soil behavior type zones are represented as radii of a circle. And as that radius or I sub C gets larger and larger, you move to finer and finer grained soils. So again, gravelly sands up here with a low I sub C value down to clays, silts, organic soils with a high I sub C value. The soil behavior type index is given by this formula shown here between normalized cone tip resistance and normalized friction ratio. It is an iterative process to calculate I sub C. The normalized cone tip resistance QTN, shown in this formula here, relies on this normalization exponent N, and N depends on the soil type. And so the calculation of N relates to I sub C. And then based on the I sub C value, you go back and recalculate I sub C, or based on the N value, you go back, recalculate I sub C and the normalized cone tip resistance value. And it takes a few iterations before they converge. Typical values of N are 1 for clays and 0.5 for loose sands, and N varies between 0.5 and 1. So in order to do this iteration, typically start with an N value of 1, and then iterate on the QTN, I sub C, and N until convergence is reached. Just a few iterations usually. An example of running through these calculations with some example values is shown in this slide here. In the end, it takes about 3 iterations before you see convergence, but you end up with an I sub C value of 2.72, indicating that we're in zone 4, which are silt mixtures for the soil behavior type. An example of some data from our Northeast Portland research site, looking at the soil behavior type I sub C value shown here, and then with some nice coloring to indicate to which zone the soils are falling into, and we can start to see some patterns in the stratigraphy come out. We see that the I sub C value below about, this is in feet, so below about 3 feet, we have an I sub C value that goes between about 3 down to about 2.8, 2.7, back up to 3, relatively small changes. Based on a lot of augering at the site and sampling. This is generally a fairly uniform silty clayey unit until about 36 feet, 35 feet, where now the I sub C, it drops to about 1.6, 1.8, indicating that we're in a sand unit below 35 feet. Another classification for soil behavior type is based on the behaviors of these soil groups. And so it's that same normalized cone tip resistance sleeve friction ratio, but now those zones are drawn as behaviors. And so we have sand-like soil that's dilative or contractive. This is the boundary between contractive and dilative soils, with clay-like dilative, clay-like contractive, and then also transitional soils. And one last soil behavior type relationship to look at, or correlation to look at, this between normalized cone tip resistance and excess pore water pressure U2, divided by effective vertical stress. And this correlation, or this soil behavior type, it is designed to differentiate between the excess pore water pressure generated by the soil itself and the excess pore water pressure that still exists due to drainage conditions of the cone. So those are several soil behavior type correlations that you can use for looking at cone data. It's worthwhile to look at all of them, see where there's patterns between the data, see how they agree or disagree with other data from the site, such as drilling, sampling data, geology, and then choose the one that best suits the needs of your project. Now, soil behavior type and stratigraphy is one type of interpretation we can go with the cone. Now onto soil properties. And there's a whole list of properties that we can interpret from cone data, shown here. Some of these work well for sand, some of them work well for clays, and some work well for all soils that the cone can be tested in. I do not have time to go through all of them, but I will give an example of correlations with unit weight. And the things to consider with using the unit weight correlations are also what can be considered with using the other correlations as well. And so a lot of CPT-based soil property interpretations are based on empirical correlations. So we have lab measured properties of the soil that we then relate to the CPT data for these soils. When you're using these correlations for soils, you want to ask yourself or to look into the literature of how these relationships were developed to understand what are the reference data that these correlations are based on, what types of soils are included in that reference data set, and what type of testing was used to characterize the soil property. And when you're looking at this, you're asking yourself as well, how does the soil from my project and my site fit into this correlation? Is it similar to it and therefore can be reliably used? Or do I have soil that deviates from the reference data and therefore I cannot reliably use this correlation? Another thing to look at with these correlations and the reference data set is the scatter that's a part of the reference data. With the correlation, we tend to get one value or one relationship like this shown here. But by understanding the scatter or the range of data that are in the reference data set, you can understand the range that your value might reasonably fall into, as opposed to just that one. So consider the data and consider the scatter that the relationships are built with. Looking at unit weight, we have several empirical relationships that apply for standard clays, silts, and sands. In this case, the relationship from the ConeTech manual relates to effective cone resistance, and I'll show some others that relate to sleeve friction. And so what we see as the correlation works out with this reference data set, we see that as the effective cone resistance increases, the unit weight of the soil also increases. So cone tip resistance increased cone tip resistance correlates to an increase in unit weight. What we note here is that there's some soils, as noted nicely in the reference, that are not included in this relationship. The orange dashed line is the correlation. This is the reference data set. And we see that these soils, organic peats and diatomaceous mudstone, don't fit with the correlation, and therefore should not be, if you have those types of soils at your site, should not be using this correlation for those soils. This is a correlation between the unit weight and sleeve friction, and we see that an increase in measured sleeve friction correlates to an increase in measured in unit weight. And again, we see the soils that are not part of this reference data set, organic peats and diatomaceous mudstone. This is a summary table of 3 relationships or correlations to unit weight and cone data that relate sleeve friction cone tip resistance to unit weight, as well as a summary of the soils that these relationships were developed with. And so the recommendation in the ConeTech manual for interpreting CPT data is to use an average of these 3 approaches. And then also noting that these soils do not include, these relationships do not include diatomaceous soils, organic soils, or cemented soils. And so we've gone through unit weight interpretation and soil behavior type interpretation. And now I have an example for interpreting cone data that I developed in a collab that I'll share with you. And this is interpreting CPT data at a liquefaction site from the Kahramanmaraş earthquakes that took place on February 6, 2023 in Turkey and Syria. This is from a site where reconnaissance documented significant building settlements, as well as liquefaction ejecta following these earthquakes, to indicate that there was significant liquefaction at the site. I was part of a team that collected subsurface data from one of these sites where there was major building settlement. The plan view of it shown here. To collect CPT data so that we have a better understanding of how CPT data relates to liquefaction triggering and how we can relate it to predict building settlements. At the site, we took about 15 CPT profiles, and we'll look at interpreting this one profile here, CPT ISK05. This is a link here, the QR code, the link, that brings you to a Drive folder, and that folder has the slides from today's presentation, the CSV file for the CPT data, and the collab to interpret that data. And so the collab, it's based on Python coding, and it's run, the code is executed in kernels to process the data and also to visualize and interpret the soil behavior type for the CPT data. The objective of this script and these kernels are to interpret the unit weight of the soil. We're going to plot an effective stress profile, including an estimation of the water table depth, and then we'll make estimates of the soil behavior type and look at the various soil behaviors and soil units that are present at the site. And we'll also make an estimate based on a soil behavior type index less than 2.6, indicating sandy soils, where we think that that soil unit that liquefied exists. So the objectives, as we see here, we're going to interpret CPT data from ISK CPT 05, identify major soil units present and their depth, and then interpret which soil unit was most likely that critical liquefaction unit. So there's some more instructions for how to run these kernels. The section in white, that is notes on how to run the scripts, if there's any inputs needed by the user and what they're doing. And then in order to run each of these kernels, you press the little arrow button at the side of the kernel, and it will run. And then you do these successively moving down through the scripts. I'll note, while that one's running, that we collected these data with support from the National Science Foundation, and then the CPT data from the other profiles and other sites are available on Design Safe. The link to the project is here. So that first kernel ran, and then this second kernel, here you're inputting the units that are used, that your CPT data come with. In the case for these data, the cone tip resistance is megapascals, sleeve friction is kilopascals, U2 is kilopascals, and the depth is meters. The area ratio correction for the cone was 0.8, and we're not making an elevation correction for this one. In this section, we're choosing the input data file. So we start the kernel and then choose the file. And in this case, if you navigate to the folder with your cone data in it, you can upload that data. Yes. And then you just run through these other sections. I won't go through what all of the sections are doing and their purpose. In this section here, you'll get a plot of the CPT data, cone tip resistance, sleeve friction, and U2, as well as the interpreted static water table. In this case, we can see that in this upper unit, we're getting about hydrostatic water conditions measured with the cone. And then if you want to, you can also change the water table depth. You can try making it 2 meters, rerun the kernel. And now maybe we see a slightly better fit with that soil with the water table at 2 meters depth. Better fit with the U2 pore water pressure. Continue moving through. There's descriptions at the top for what each kernel does. And there should also be a note whether you, as a user, you need to input something or that you can input something. Move through. These are functions for interpreting unit weight based on the CPT data. Here, there are some inputs. And in this case, you can make changes and input different unit weights and different depths that those unit weights correspond to. It also plots out the unit weights. So here we see elevation of the CPT profile versus unit weight in kilonewtons per meter cubed, or interpreted unit weight. The 3 different interpretation methods are plotted here that we showed in the presentation, as well as the average of them as recommended in the ConeTech manual, which is shown in the kind of the dark black line. And then based on the interpreted unit weight, I've interpreted approximately the approximations for different units and their unit weights. So even though the CPT data are going like this, there's noise in the data, maybe from variability of the soil, likely from variability of the soil, and a bit of noise from the instrument itself. We can then generalize this to approximate a unit weight over different depth intervals, which I've kind of done my best to approximate here. But you should go in and make changes and play around with this yourself and see if you can, if you interpret it differently and have a different fit. So those inputs go up here, where if you want to change the value of the unit weight unit, the top and bottom of it, and then you can also add more units as well if you think that it's better suited with 6 or 7 unit weights as opposed to 5, as I've shown. From those unit weights and the depth of the water table, we calculate and plot the unit weight profiles for the site, effective total stress, total vertical stress, vertical effective stress, and pore water pressure. And now we're getting into the soil behavior type interpretation. This kernel is going through calculating I sub C and other soil behavior type indices. And now we're getting a plot of the soil behavior type indices and their profiles. We can start to see that there's different zones that might correspond to different soil behavior type units. Maybe one where we have a relatively low I sub C value down to about 10 or high IB value. And so from here, you can start to pick out where you think those units exist and the depth of them. Like let's say this one goes to about 9.9 or 9.8 meters is the first. Maybe there's another one here down to about 15 meters. Start to get a sense of that. And then also looking at it here on these plots to give an idea of where the data are. But then based on those profiles, you can input the bottom of the units that you're observing, the bottom elevation of them. Here I've interpreted those units to be at -10, -15, 18, and 28 meters. Run that kernel, and then this is going to plot out those units separated by color to get a better visual of them. So we can see based on with the color that helps us pick them out, we can see the way that I've initially interpreted these soil units in terms of soil behavior type, and see how they're plotting on the soil behavior type charts and if there's agreement between the different zones or not. I'll note for now is that we see that this upper layer to about 10 meters tends to cluster in zone 6 with sands on both of these plots, and it plots as essentially drained sands on the Schneider plot, which is generally consistent with the others as well. We might see that there's turquoise and purple units. These two here are plotting similarly on these soil behavior type charts. They could potentially be approximated as one. Or maybe we're saying that there's a bit of a transition there. And then we see this other unit between kind of like silty, clayey soils there. And so what you can do here, I've also got these zones here labeled so that you can reference those back to here. So you can go back and make changes to the depths that are input here. Let's say we think that this one is actually 9.5 or 9, say 9.5. Rerun this kernel and then rerun this one to plot it and see if we like the way that they plot any better now that we've made that difference to the depth. All right. And so we said that an objective of this was to look at which unit we think was likely the critical liquefaction unit or the unit susceptible to liquefaction based on the I sub C value, the unit we identify as a sandy soil or sand soil. And the I sub C value of this upper unit to about 9.5, 10 meters depth, that has a low I sub C value, indicating, and less than 2.6, indicating that it is a sand soil, sands, clean sands to silty sands. This is likely our critical soil unit susceptible to liquefaction. So this is the collab. You have access to it in your in the Google Drive folder that I shared. Take it, make a copy of it, change it, give feedback. Happy to hear it. So final thoughts on the cone penetration test. It is one tool in your site investigation toolbox. You want to understand the advantages and limitations of any tool in your toolbox and evaluate those all and how they work together in order to interpret the needed properties, stratigraphy, subsurface conditions for your site and your project. From a CPT data profile, we can interpret stratigraphy, soil behavior type, and soil properties from that nearly continuous soil profile. We can and the CPT data should be interpreted in the context of site geology, other site investigation data, and the data used to develop the CPT interpretation method. You want to bring it all together to create a model for your site, or I like to say a story for your site. Here's a list of useful resources if you want to learn more about the cone and its interpretation. The ConeTech Design Parameter Manual is a nice comprehensive document for interpreting cone data. And then finally, an acknowledgement to Dr. Jason DeYoung at University of California, Davis, who has been helpful for developing these slides and learning about the cone. Cone Tech, who's been supportive of our research program where we get to go out and push the cone at our site and learn more about it. And then the many researchers that are developing CPT theory, relationships, and correlations, and then the engineers that are using the CPT and using these relationships and correlations and expanding its use in practice. So I hope that you all had fun, that you learned something today in summer school, and I look forward to seeing you all again.